Hello everybody, welcome to another stream. How are we all doing? So, last stream we was looking at the, let me just get to the right directory there. So open up a new tab as well. Cool. So last stream we were getting we was looking at the renderer and see how many ellipsoids we could push. And we're trying to really push at least a million through the renderer and get it to be good enough. And we're looking at it and this takes about, for these million that we're trying to push through the renderer, I think. Wait, we've got to actually zoom out a bit. Well, it's very difficult to judge. But yeah, it's about like, I don't know, 7 milliseconds in total. We've got for the ray tracer it takes 6, which does obviously material shading at the same time. And then plus the millisecond to sort all of them. And it got me thinking that, you know, maybe there might be a faster way to render all of the opaque objects. So we threw together a very simple shader for... Is it even running? Yeah, it's called Ellipsoid Opaque Render. And essentially what it does... I don't know, my laptop battery's... Oh no, it's my laptop. Look into the Wi-Fi again, damn it. Alright, I guess I'll gradually look back at chat. Oh well, put that laptop away. So, effectively, this just, at the moment, puts a little box around every single ellipsoid and will render, it will do a ray trace against it per pixel for that little box it puts around it. But I'm doing it in compute shaders. So right now that little box is a minimum 32 by 32, but it will then do the rest of the pixels in a for loop, basically. So for ellipsoids which are smaller than 32 by 32, this is not an optimized shader for that. And that's what I want to hope to get started on today. So essentially the way we're doing it is, I guess this is inspired by the nanite renderer or other renderers which have done atomic min stuff. So if I look for opaque, here it is, right, we've got 32 by 32, it's just Morton swizzled. What's that noise? Oh, it's just when this is running, isn't it? Yeah, for some reason it makes the sound card do that when it's running too much. I don't know what it is. Hey there, Hedge. How's it going? Let's read your question. Do you have any unique mechanics which affects the engine? If you were talking about game mechanics, then no, because I don't really have a game at the moment. But it's the unique thing about this engine right now is that it renders ellipsoids, and that's the unique thing about it. I wouldn't really call that a mechanic though. But yeah, there'll be some built-in editor and things, and we're building like editors and such, so you can make everything within the engine, if you will. Yeah, so we get a 32 by 32 tile, and then it goes over all of the 32 by 32 tiles that it takes to render this screen bounding box around the ellipsoid. And then for every pixel, it does a reverse ellipsoid, and then sees if it. Yeah, it does a reverse ellipsoid, and then it sees if it hits it. And then if it doesn't hit it, continues it. If it hits it, it writes to... Well, this is a spoiler. it writes to the depth buffer for now. This is what we've been testing, is the depth buffer write. And it writes to it by doing an atomic min for the coordinates. So there could be tons of ellipsoids rendering at the same time, all overlapping each other, and it just atomic mins into a buffer. Now this is okay for just writing the depth out, but the problem is we want to write more information than the depth. So what we're going to be doing is constructing a thing called a visibility buffer. This is what engines use these days. There we go, I can spell it. And essentially what you do is you make a buffer that's filled with what's known as like an object ID, or like maybe like a primitive ID, which can be translated to mean triangle ID in most renderers, but in R1 it would be an ellipsoid ID, or it's an index, right? So for that we need 32 bits. But what we want to do is render the closest object. So we need the depth in there as well. And typically in the visibility buffer, you need the depth anyway. Like in this ray tracer, we need the depth. Because the whole point of a visibility buffer is that you can, from the information that you have in the texture, you can completely do all of the passes after that, like basically material shading and whatever. You can construct normals, like surface normals. You can construct surface hit position, you know, and get everything you need. So what we need is actually a U64. Now, I spent my lunchtime adding enough support into my custom compiler to get 64-bit textures working with atomics, and then I realized that actually we would be losing support for a lot of hardware, which is a shame because it is an extension, unfortunately. And if you take a look at, for every single Vulkan device, there is, hang on a minute, let's just let it load because there's just so many Vulkan extensions now that it takes ages. So there's an image atomic, this one here. So 22% of all devices support 64-bit image, and obviously 77.7% don't. Now, that's an extension, right? If you go to core, so core features, so for all the devices that support 1.0, right? Which obviously is everything that is ever supported Vulkan. 50% of them support int64s. Now, for all of the devices that support Core 1.2, this is another one which it will be useful to keep note of. 67%, but right, basically 70% of them support integer 64 atomics on buffers. Okay, so this is extremely useful information to know. So this means that if we don't use a texture, but use a buffer instead, then it means that we'll be able to support 64-bit atomics and do our atomic min operation with our depth in the higher bits. And then when we do our atomic min, it should sort, everything should be in the right order. So it means the closest thing will be put to the closest ellipsoid index will be put to the screen. So with this though, we've got to be very careful, because what are textures? Textures are an optimization on a buffer, basically, right? A buffer is just a range of memory. So I did post something in the Discord. I posted, we need to basically do our own custom swizzling or tiling. So all textures do is they make it such that when you pass in a 2D coordinate, it translates it to a 1D coordinate, but it's not. I'll leave a link to this if people want to read it proper. Hey Swank Funk, how's it going? How do you get started to learn Vulkan? Well, I wouldn't say there's an easy way, but let me just ask you a question first. Have you built a renderer in something like OpenGL or DirectX 11 yet? I guess would be my first question. Because unfortunately with Vulkan, it's a very sort of, I wouldn't call it low level, but it's an API which is a very, it's not very, it requires you to do a lot yourself, but it's not low level. And you're in control of a whole lot of things, and it makes that, and you don't really sort of know what it's mapping to at a low level, and it's a lot to learn and really wrap your head around. Yeah, not accessible, but it is possible to learn, and I wouldn't put people past trying to learn it. What I would try to say is you're better off learning the sort of more higher level aspects of graphics programming first before you dive into using Vulkan. Yeah, so you're better off learning about the high level, like basically what you're trying to build in Vulkan. You're trying to sort of like use the things above that and be more familiar with those and how to architect like a whole renderer and what Vulkan is used to do. And then also you're trying to learn about the low level of like how a GPU works. And then once you have those two sides of the puzzle, learning Vulkan becomes far easier. But if you just learn Vulkan, it's like you're gonna have a really hard time. I had a really hard time because that's what I did. I learned Vulkan and it was so complicated and crazy. But so if you haven't learned a graphics API before, I recommend starting with probably something like SDL3 and use their they've actually done a release today, 3.2, and they've got a sort of relatively new GPU API, which abstracts over Vulkan, Metal, and DirectX 12. And I recommend using this thing, building a few like 3D renderers in it, and start to look at the ARM Mali GPU training series. This is an amazing playlist. It teaches you about mobile hardware and desktop hardware and how they sort of work under the hood. And this is very useful knowledge for knowing how Vulkan gets implemented, basically. Like what is Vulkan abstracting over? Because that's the problem when you learn Vulkan. No. So SDL3, they released an API for... They released an API. Hang on a minute. I hit the wrong one. Oh, that's good. Yeah, they released an API. Oh, I've got to go to the include folder because it's a properly structured C library thing, isn't it? So they've got this SDL GPU and it sits on top of Vulkan. And it's about the same level of abstraction as like DirectX 11 or whatever, but it goes over the newer APIs and it's cross-platform. And it's probably a bit better than DirectX 11 maybe, I don't know. I've not really used it. Them both actually. But it's just a GPU API. So you can do 2D or 3D in it. So yeah, I recommend looking at this basically. Or the other one is Web GPU, but I recommend SDL3 over the Web GPU though. And yeah, if you have any questions about things you want to talk about, stuff off stream, feel free to come into the Discord. Plenty of people in there that can help you with your things. So yeah, because we don't have that texture coordinate, so because we're using a buffer instead now, to give us more support for integer 64 atomics, the way textures work under the hood, and I did a pop a link to this in the chat. Yeah, I did. Good. If you store things in row major order, that's going to be terrible performance for this shader, isn't it? Because this shader gets a 2D. I think also a good way of saying it. Maybe I can take one of my images from the screenshots and I can... This would be an alright one. Although it's transparent. Here it is a good one. Kurita. Here we go. So imagine we're trying to render this ellipsoid here. What we do is we put a box, essentially we have this sort of box around it, right? And we're going, the way we've dispatched our, or we've Morton swizzled it, isn't it? Yeah. So we've swizzled our dispatch index such that our pixels get dispatched in a sort of Z-curve order. So in a every 4 indices, every 4 pixels will go in this sort of like 2 by 2 order, and it does another 2 by 2. I think it's like, maybe it's a Z like this. I don't know, but they're basically like little Zs, right? And then when it's done one Z, it does another Z in a sort of a Z pattern, right? And obviously if we're writing to pixels within the same wave, so a wave is like 32 threads, right? Well, 32 of them is 8 by 4 pixels, right? So if we're trying to write 8 by 4 pixels out in this sort of Z order, well, if you just write that to a buffer, the buffer's pixels will be in a sort of a row. They would do one row at a time, right? So that would mean whenever you're writing to sort of this region here in about one wave or whatever, it's like 8 by 4 pixels or something like this. It could do, wait, 8. Oh, there's 8. 8 by 4 pixels. You want to make sure that these are all close to each other in memory as possible. So if we sort them into this sort of Z-curve order, it should be more optimized to write into the buffer basically. So we have to swizzle our buffer such that the coordinate isn't just a sort of row or column by row mapping, if you will. And that should be more optimized. So we're going to test this out. So what we're going to do is, first of all, create the buffer. We'll just do the sort of standard way you'd flatten a coordinate by doing like y times width of the texture plus the x coordinate. And then we'll just see what the performance is compared to writing out to the 32-bit texture and see how much worse is it writing out twice as much memory but also in a flat buffer, and just gauge performance that way. And then we're going to actually swizzle the texture or tile it, or maybe both, and then see how that performance compares. And then we'll go with actually trying to write more ellipsoid renderers that would be specific for smaller smaller ellipsoids because this one's good at 32 or 32 and more, because it's a minimum will write out that a minimum has threads allocated for 32 by 32. But we probably want to make it such that we have ones which are very good for targeting ellipsoids, which are actually like 8 by 8 in size, or 1 by 1 in size. They're very different compute, well, they're slightly different compute shaders. Those things there. I need to have a look on some C#, Python, or pure Rust for some engines. Okay, that's cool. Well, there are some, the Rust engine space has taken off lately. So there's plenty of people writing engines now in Rust. I'm not sure about C#, to be fair. Okay, so let's get going with the test. So go to graphics. What we'd like to do is create our image. So we're going to call it the visibility buffer. So let's go to the graphics strut, and we'll call it the visibility buffer ID. All right. And what we're going to do is create it based on, it's got to be resized with a window. So we need to make sure that, it's got to match the scene dims, isn't it? So we'll just create it with a 1 pixel, so 1 times size of U64, because it stores U64 in there, visibility, and then visibility buffer. Cool. Now, we need to find, actually, this can just be a temporary resource. It doesn't have to be a static resource. So temp means that it gets allocated at some point during the frame, and then it gets deallocated at some point during the frame. And then the memory can get recycled, so it's quite nice. So we can deallocate it before the end of the frame and then recycle the memory and use it for other things. So very powerful stuff. And this will mean that when we do a sort of a scene texture, what we can do is do it here, right? We can say temp alloc scene dims, so x times scene dims dot y. So I completely did this wrong. It's GPU temp buffer alloc, and voila. Wait, we need to say multiply by size of U64, okay, because it's in bytes. So that will get the buffer allocated, which is great. Then in that sort of opaque render, which we're going to rename to sort of visibility buffer render or something like this, all in good time, we're just measuring performance right now. Visibility buffer ID. So we need to pass in the scene dims. No, we don't. So go to the shaders. So yeah, this shader runs, each thread group gets an ellipsoid, and then it just tries to render every pixel within that there. So if we do the graphics global scene dims dot x, that should be good enough. So let's put it down this sort of row major order, I would say. Maybe I'm getting the wrong way around, but there we go. Cool. So let's check what the performance is now. So the performance was competing against was, the old one was about 4 milliseconds. So this one is still 4.15 milliseconds to render out to that buffer. Interesting. So if I was to enable this one here, and then comment out this one, I wonder if we'll need to do swizzling then, Because that performance is kind of... Maybe we'll do the swizzling later. Right, apparently this one is like about the same sort of performance. Strange. Right, what happens if I don't swizzle? What's happening with my local chord? Yeah, let's say if I don't swizzle and... the Mon Z curve swizzle. And then we'll put it to 32, 32. Try that. Let's see how well that behaves performance-wise. Right, that's a bit worse. Interesting. So I wonder how much better performance we would get if we were to actually swizzle this into... Be interesting, wouldn't it? We could have a bit of fun here. Hey Lupo, how you doing? I'm not doing bad, thank you. I'm actually doing quite good. Yeah, I've been feeling quite good lately. Got tomorrow off work as well. So I'm gonna go to the gym with my wife. We're gonna have a good time. She's recently joined up with the gym again since, you know, she's been a bit pregnant and feeling a bit ill, so she's not really feeling like for gym. So yeah, she's back into it now. Got me a 3-day pass, so I'm going with her. And so that'd be cool. So we get to do that together. That'd be nice. I didn't find any active cross-platform engine or toolkit in Rust. Oh, there's plenty in there. Isn't the sort of current one that people raving about is Bevy, right? Rust. Bevy. It's got 2D renderer and a 3D renderer. I don't know how good it is, but I think they're quite... This is probably a place to start. Or just come down and learn some C, man. Will you switch to Java when it's released? I don't know. I'm not sure. The problem is like C is like just good enough, and I've written my own C compiler now for shaders. If John steals my idea and, you know, makes a shading language, makes Jai also be able to do shader code as well, then that would be more tempting. You know, right now it's just John working on the compiler. It would be great if it was more, you know, open and available to everyone and stuff, right? And yeah, I think his language is yet to go through a, you know, he's going to be doing like a bit of a refactor to it, isn't it? Because there's just like weird like little bits of syntaxes and that in places. But yeah, I guess further down the line, if it's, you know, maybe. I don't know about all the extra complications they put in the languages. I have to look at it, to be honest, because one of the reasons why I haven't gone to these other sort of new languages is they just bring in a lot of new ideas which are not really tested, and they're just, yeah, they don't really provide me anything better than just writing stuff in C. So, you know, like, I know people got really like hyped about Zig and stuff. I know Zig does some really cool stuff, like in terms of like the low level things they expose, like the intrinsics and that, but and stuff to do with the compiler, how it sort of works. But all of the sort of high level-y stuff and the very power user features, I basically do not want. And I think they very much make the language far more complicated than I would like. And it just allows for people just to be silly. And you know, the thing is, I don't want a language to have type inference in it. And because it really gets me when I read some code and I just can't tell what type the thing is. And you know, I guess I've read the whole code myself anyway, but if a language is to replace C, it can't have type inference in it. But I know C recently just got type inference, so there we go. C is dead now as well. C23 killed C. But yeah. We'll see. We'll see. How about you, Lupo? Are you going to be on Jai? Have you got the Jai beta already? Are you a Jai guy? Right, to see if this swizzle thing is going to get us any better performance. We need to make sure that we organize our things into these sort of like tiles. And yeah, so I think we did a 4x4 tile. I think this is the maths here. You figure out what tile you're in, and then offset into the tile, that might be it. Yeah, let's try and do some sort of like tile addressing and see if that will improve the performance. So the performance is about 4.15 milliseconds. So if we were to sort of figure out, so we tile it such that, so we've got 64-bit number that we're writing out to this texture, right? So that's 8 bytes. So 8 bytes is a cache line of 64 bytes. But unfortunately, 8 is not a 2D number, like a square number. There we go. See, it doesn't. So you're not. So the close. So you've got 2 by 2, right, which is 4. But that means there'd be half a cache line. You fill up half a cache line in a 2 by 2. Or you can have a 4 by 4 and you'll fill up a whole cache line. Let's do it as a 2 by 2. Let's see that. Let's see what happens. So tile dim 2. So tile x coordinate would be pixel coordinate dot x divided by tile dim. Y. Alright, so what's the logic again? So we want to figure out the number of tiles. Right, so divide round up. Tile grid dim. 4 divide round up. So that'll be the width of the texture in pixels divided by tile dim. So the logic is you flatten out so you figure out tile base index, which would be tile y times by tile grid dim times by tile or plus tile x. So that'd be a tile index. No, I was just curious. I think he gave access to beta only highly skilled people. Oh, no, 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 no. John, if you go and ask him, I heard people who are like just learning and they just go, "Hey, John, I really find just, they basically just give him some compliments because they do generally appreciate the stuff they look up to him, right? And then they go, I'm learning at school, but, maybe I'm learning OOP and I don't like it, but I see your stuff and it's really cool. Can I have access to your compiler?" And he'll give them access. There's a few people who have done that. It's quite nice about that. But yeah, other than that, he generally does want people who are looking to write their own engines and stuff, giving it a go. Of course, he does. But he's good at just giving it to people who ask nicely. From what I've heard, right? There's one guy who's making a game engine and a game enjoy. That's cool. Oh yeah, I've seen that guy. Yeah, I've raided him a few times. Yeah, he's got like a little game in the corner running, and it's like a top-down thing. Yeah, that's good. The hard part with game creation is AI. I don't know if the logic. I don't know if some logic games is rule-based and how to do with races and such. I don't know. Like things are just hard until you try them and do them right. You know, when you get into graphics programming, I'm sure you'd be like, "That's hard." Oh, did you ask about post Discord? Sorry if I missed it. Oh, you posted on the Discord, right? Ah, I see it. Yeah, I'll catch that one after. It's good. But yeah, AI is there's like different ones like rule based stuff and that you just got to give it a go, and it's probably actually a walk in the park in comparison to a lot of other things in game dev. Maybe I might be on the look. I'm looking at. I've done it a few times. Yeah, I ain't got my laptop working today, so I won't be able to see you guys messaging unfortunately right away. But I'll be here. I'll ping back. Tile width. Yeah, multiplied by the number of pixels in a tile. So tile pixels count is tile dim squared. Yeah. So tile base pixel index, tile index multiplied by tile pixels. Yep, that's the maths. And then we basically add within the tile. So the actual pixel index now we need a sort of a tile pixel x, and that's mod. Now because you're doing because this is a power of 2, these divider mods become shifts and ands. So they were actually a lot quicker than that. So then your other thing is now actually the pixel index, and that'll be tile base index plus the tile pixel y times tile dim plus tile pixel x, and voila, tiling. So now hopefully things within the same 2x2 are inside the same cache line, but also things within the same, but also things in the same wave are all next to each other in memory. So it should hopefully bring us better performance. So I'm interested though, because the performance of not swizzling and compared to using an actual texture, it was quicker to use it was the same speed using a buffer and not swizzling. So I'm really confused there. So now we're going to run it and see if it's even better than a texture would have been. Right, it's just the confusing thing to me. Right, it was slower. Okay, so it is slower there. I didn't. So I don't have to swizzle it. Maybe we can change the tile size. So so that was 4.3 milliseconds there. The one that it was earlier is 4.15. So now we're going to try and up this to 4 to make it 4x4. See if that's better. I don't know if it's still the extra maths that we're doing. I thought the memory would be a better enhancement. Yeah, that one's better than it was. Nah, it's about the same. Yeah, I don't know if we increase to an 8 by over, that's going to help either. That's a bit bizarre. But yeah, that maths looks correct to me. These probably get optimized out, right? Shifts. They must do. I would hope the compiler's doing that. Maybe it could be better laid out a bit by using like proper Morton code and stuff. No, maybe. Yeah, okay, it's not getting better, increasing the tile size. Right, so apparently we don't have to swizzle anything. And it's fine. So if I was to literally delete all this and put it back to what it was before, which was simply just y times width plus x. Apparently that's good enough. So because we're running out to a buffer instead of a texture, we cannot see it in our super lovely texture viewer. Oh. Okay. So right, let's do it proper. So U64 pixel. So where's the ellipsoid index? Yes, we do this as U64. Shift this shift F32, and then we OR on the ellipsoid index. Easy peasy. Throw that into here. So the problem is we're running out of buffer instead of a texture, and we cannot view this in our super lovely texture viewer. So what we're going to want, right, is 2 new super lovely shaders, or just one lovely shader where we say visibility buffer debug. Visibility. Let's close that now. F Heroes 2 engine comes into more difficult AI in those. I'm not sure what that is. What's F Heroes? It's a game. Interesting. Right. Yeah, I'm not sure how difficult the AI program is in that game. At this point, I don't think I care much about language that much, as long as it gets the job done. Yeah. What language are you using at the moment, Lupo? Yeah, the things about me, I am very opinionated. I will say that. But right, how do I want to structure this? Yeah, 64, and then I do the 8-byte swizzle. Yeah, so I'd say I'm very opinionated about languages and things, but C, I can get over the stuff it does wrong because I literally just avoid using it. And there's not much of it. C++, there's so much in there that I'm even tempted by some of the stuff because it is, gives you good power. It gives you a lot of power, but then like the way it's implemented is just enough to bite you in the just enough to bite you back later. And even if it was maybe implemented a bit better, some of the new features, some of the high-level features like templates or something, maybe in a newer language templates won't be as bad for like compile times and things, but still, you would over-engineer things because you've just templated everything. I don't think I have the temptation to template stuff anymore. I think I've removed that one from my sort of habits. But there's other things, like a good old closure or something. Put that in a function somewhere. Closure gets too big and it's unreadable. Makes your code more unreadable. I'm content with Unity C# at the moment. Cool. Yeah, people find C# like a lot, like as an easy language. I don't like the namespace and class sort of them forcing you into that. I do see though how it's sort of a cleaner C++ in a way, but it is very OOP, and I just despise OOP, so it just doesn't go down well with me. But I see why people like it because they just taught OOP, and it's nicer C++. Well, not really. You can write engines in whatever you want. People write in JavaScript. But I like the low level side of development. Right. That's where that's why I got into games. It's like, well, no. I like obviously like I like games. I wanted to get into programming. And then I was just like doing JavaScript, and I was like, how the hell do you make a binary? A binary sounds cool to make. How do you make that program you can double click on? Why isn't my JavaScript a little program you can click on and execute? And yeah, then I learned obviously you need to do C++ whatever to do that. And I was like, you know what? Let me try and learn this. And I saw pointers, and I was like, damn, these pointers are so hard to learn. I'm never going to leave JavaScript. And then a week later I learned pointers. But obviously things are hard when you first see them. The more I do C++, the more I admire C++. I mean C. That was a good one. But yeah, I do like aspects of C, right? People don't like the way you have to declare stuff in order. But the way you're forced to do header files is kind of nice for like documentation purposes, right? You have a sort of zoomed out view of your code by going into a header file, and you can see all your functions. And it's kind of nice to look around just to see stuff in that view. And people be like, that's a text editor feature, but I also like scrolling through code on GitHub and not downloading it and seeing explicit type names here. Because people who write in new programming languages never write their type names down, and the code is just so unreadable. If I haven't got it in a text editor, and people are like, that's a text editor problem, get it in there. I don't want to use a damn text editor to read a bunch of code and get it all set up. I just want to get in there and read some code on the internet sometimes, So yeah, we just want to read from the visibility buffer, because it's literally a buffer, and write out to a texture because we're not using textures. So we can have wider hardware support, because not all hardware supports 64-bit atomics on images, but it does on buffers, and apparently its performance is kind of the same on AMD at least. Probably need to optimize that later. Let me write this down. 2D, we might need to optimize. This is the problem with not using textures. Optimize the swizzle, this sort of swizzling of the texture of the in-memory layout the reading and writing into the text as we're writing a 2D image, some kind of swizzling of the seems like a good idea, but for some reason yeah, okay, let's just leave that. Seems like a good idea. Future me to have a look at. Nice. So what we would like to do is make a sort of debug view, which is literally going to read over that buffer and turn it into textures, two textures. So this visibility buffer is I got used to spelling this word. There's just so many I's in there, it's just mind-blowing. Visibility buffer, and then so it's read-only. And then we have a read-write texture 2D. And that is a format E32 float, that'd be for the depth. And then we want a 32-bit int for the ellipsoid indices. Nice. So we'll only really run this for debugging purposes, but in the future we'll yeah, we won't be running this one. Let him release or anything like that. So we simply just read the U64 pixel from BC visibility buffer. We read ucoord, this pixel index here. And then we simply extract out depth. So that'll be bits to this sort of float. We take the pixel, shift right by 32, and bam. There we go. Then the other one is the ellipsoid index. And that is simply pixel and nice. And then it's simply just, run out to those textures. So store texture 2D, format 32 float. So the texture that goes in is, in this case, depth. We pass in the index, which will be eChord, and the value should be depth. Next up, we copy paste that line and do a U32 uint. Sorry, 32 uint. And then ellipsoid indices, then ellipsoid index. So that'd be a nice shader just to help debug this buffer we've rendered into and view in our super lovely texture viewer. So let's go ahead now and launch that shader. You know, we should probably rename this guy to visibility buffer render. Alright, I'm getting better at typing that. And then your JavaScript sounds like a crime. Plenty of people have done that. Yeah. C is an assembly language that humans can program with, isn't it? Oh, no, not really. C is an abstraction on top of many computers. You know, it's definitely high level, but yeah, it's definitely a high level. Like, you don't directly write like into registers, and you know, because what's pretty great about assembly is if you wrote all your code, you could just store something in a register and never change it, and just have this sort of 8-byte pointer or something that you can just have access to from any function, and it's just there. Like, there's stuff you can do like that if you just did assembly, whereas if you use C, there is an abstraction, and you have to follow its rules and things that is laid out by the language. And if C doesn't have a feature to do the thing, typically a compiler will have an extension. So there is stuff like, yeah, there's plenty of like intrinsics in the Clang compiler and stuff, but it might not have ones that you use to do the things you want on that particular hardware. So you literally have to drop down to assembly and get in there and do it with inline assembly or a separate assembly file that you simply link into your main program when you compile your C code. That sort of stuff. Oh man, this is going to be awesome. Okay, so we're just going to output to output 2. We've tested. So there you go. We write out to a buffer instead of a texture. Wow. Okay. And now we just simply copy paste this and do another dispatch. This time over the full screen. Oh, messed that one up a bit. And the other one is was it debug? Is it debug? Yeah. HCC shader. Nice. So this one needs a sort of debug constants passed in. And we're going to pass in the visibility buffer as read-only. And then read write is going to be the, so we don't have the ellipsoid indices texture ID. We don't have that. We've got to make that quickly. And the other one is just the depth texture, right? Nice. And that'll be depth. And this will be ellipsoid indices. The wrong way around. Now, that's looking good. We just got to create this ellipsoid indices buffer ID and actually instantiate it. Texture initialize temp, so it means we'll actually allocate it later. The resource type is 2D texture and the format will be 32 uint. So what's interesting is we might need to have a different viewing mode in our texture viewer to make that one look better, because it's going to look, yeah, it's not going to look great. Okay, nearly there. And give it a run. So we need to allocate ourselves a new texture, which is the ellipsoid indices one. Now, we want to make sure that we are actually writing the depth out in this pass. So what I'd like to do is not write out the depth in the ray tracer for the scene. That is currently rendering the opaques. So we've got a ray tracer which sorts everything front to back. And that currently renders everything, transparency, opaque. So we're trying to write a more optimized version. What the crap is going on here? Read-only buffer. E64 jobs are good. Oh, I misspelled something. Let me call it texture. Let's give that a go. Let me say it's closest to the metal after assembly. Right, alright, catch that loop. I can see it. Thank you so much for popping by. Right, so I think we're not writing anything good into that depth buffer. Let's have a look. So, right, it's got a depth here. Boom, my face. So that's actually not writing anything, and that shouldn't be. It's run at 0. Why run at 0? When do we ever write out 0 to the... That's interesting. So the other one is the ellipsoid. Basically run at 0 as well, isn't it? We actually have more controls, but the DPI has scaled it, so it's very interesting. Hey, pixels. Depth, right? Oh, again, this has just got a funny little line. How interesting. So clearly there's some funny business at play here. So let's look at a couple of things. Oh, are we not priming the... Yeah, we're doing an atomic min, right? We're not priming the depth buff with anything... Sorry, the visibility buff with anything good, right? So it does need to be primed with all bits on. Yep. So when we allocate ourselves the visibility buffer, we will need, or not even that, here, right? We'll need to do a GPU buffer, command buffer memset. Now, only memsets are U32 word, which is not very good. I wonder if there's a Vulkan. There's a Vulkan function for... Why do I use the internet? So, fill buffer, right? Fill buffer is only good at filling U32 words. I don't think there's a fill buffer U64. So I think we would just write a quick dirty compute shader, basically. So yeah, that only fills an U32 piece of data. So yeah, I don't think one exists. It's hard to tell. Yeah, I don't think so. So what we're going to do is simply write a compute shader out which does that. So visibility buffer in it. So I guess we could use the same constants. So we'll do another one of these. Right, but we won't synchronize. Why the rewrite? Exactly, the read only. What's going on here? Silly thing. So we'll still use the same constants, but ooh, yeah, different dispatch. Dispatch overall pixels, please. And we'll simply do visibility buffer in it. So this will cost actually, because it's... But there we go. Cool, so let's just quickly make that shader. One of them. It's one of them. So visibility buffer in it. Swizzle equals U64 max. Done. Yeah. So let's see how that goes. Damn it. It's called output, isn't it? Alright, so that should be a... There we go, it works again. So it's running the depth out properly this time, so the occlusion buffer's not buggering up the next frame around. So look at the profiler. What we see is 4.1 milliseconds, pretty good. Yeah, it's kind of a bit noisy. So 4.1 to about 4.2. It's okay. How quick is the... Right, so the initialize is actually 0.03. There's a bunch of extra buffers, barriers I put in. So you just have to ignore those. We can put the overlap in and it will reduce the amount of barrier takes up. Yeah, we can put overlaps in. So what's great is it makes it look like, so this visibility buffer, and it actually overlaps with all the stuff that comes before it. It says it takes a long time, but it just starts a lot earlier and goes slower, but with all the stuff. So there's less barrier weights. But the problem is it ends up overlapping the other stuff and getting in the way. But anyway. Cool, so that's looking alright. And what am I thinking about now? We need, yeah, so now we actually want to look at the textures. Now we've already got a good debug view. So we've got the depth, we've extracted the depth out of the high bits and put that in the depth buffer. So we take a look at the depth buffer here, wherever the hell it is. Oh, yeah, that's what we got before, right? It's, it's the thing in the middle is the closest technically because the way the field of view camera works, and things a bit further away as I go away from the center, right? Now, the other one is that ellipsoid index, wherever the hell that is, indices. So the problem is with this one is, it's a big old integer. Right, it's E32. Not really helpful, this view. So what I think we want to be able to do is make a new viewing mode where we basically so a U32 max would be an invalid one. That'd be a background pixel. And yeah, floating point is not that much to help either. So we're going to make a new viewing mode where I think it will just basically hash. It'll just hash the texture result. So we find our, I think, what were they? Yeah, white if non-zero, right, good. So we find this one. I think we can say if you hash up, if you hash up the pixel and represent that as a color, basically. I think we'll something like that. So you don't want any ranges on this one. Is white black supported? No. So white black just means like a min max basically. And then we can spend zeros for all these. Well, you could do white black, right? But based on the, nah, not really. It'd be like a clamping thing. That's what it kind of is a clamping thing. Why did I delete the other one? Right, we're nearly there. So default view mode, we're ignoring that, I would say, maybe. Now let's see across the files. So here's the actual shader which copies the texture at that point in time where you're viewing it into the texture viewer copy texture and reinterprets the pixels. So this one, I'm going to add a sort of a hash one, and we take the pixel, good point. Maybe hash isn't a good name. It might be close to the real name though, but what I want this to do is simply just take the R channel as a uint and say color equals, so I think I've got this sort of GPU, nice color. Nice color U32 ints. And just do something like that, you know. We've got to do an unpack. So unpack from basically U32 and make it a float 4 instead, and this is what I want. So we can take any integer or whatever, and it should make them view a lot nicer, especially when the values are very close together. What did I change? Cool, so we open up the super lovely texture viewer now, and ellipsoid indices, well, this just black screen, but when you use the new hash view mode, whoa, looks pretty nice, but the problem is it's very jumpy, and that's because these are not very consistent. So we've got like a nice, oh, it's a bit much in it. We've got a nice color now, but the problem is that they're not very persistent, and you can't even pause this. You know, why can't I pause this? That would be kind of nice. But anywho, say if I well, that ray tracer's taking its time. It's like 1,000,000 at 4K. Oh, there we go. So yeah, we could add a pause button to this so we could view it, but this is already a better view. It's just I don't think there's a way to make these consistent, maybe. You could take their sort of world space position, maybe, but then you've got to actually use a different buffer to get that. I don't know what else you would do, really, to make them, because they're all spawned on the GPU. Because they're ellipsoid indices that come from a predefined sort of model. So let's go ahead and make a little pause button. I think that will be handy. Don't know where you'd stick it though. Boom, boom, boom. Yeah, where we see that in the texture viewer, it should be pretty easy to add. We could stick it like above here, just pause, above the channels. Chans, as it's called. So we do a cut, or simply to add a little toggle button, with a bit of text, bit of C text. So this one will come from GPU texture viewer dot is paused. And then if it's so it's paused, play, if not pause, and voila. I don't know what else is. Oh, I shouldn't put that in there, I think. Cool. Now I just need to add the pause thing into this. So let's find another place. There we go. Boolean is paused. And then we simply just hop over to where we do the copy. So yes, it is a persistent thing. So we go if ggpu texture viewer is paused, we will return, and that should be it. And that way we can stop reading more and more versions of it from the next frame and the next frame and the next frame. Right, so it is there and it is pausing, but my issue is that it's not even a proper button because I got the no box thing on it. So let's just quickly find that. I did no box. See, I remembered seeing that text, but for some reason my brain didn't think about how the star would look. Okay, so we hop open the texture viewer. We can now view that lovely ellipsoid indices texture. You know, that should really be on a new line. But for the sake of... Oh, no. Alright, let's just correct that. So, cut left. Oh, yeah. Right. I put this in the wrong place. We're meant to have a cut top instead. Put it across there like that. Beautiful. Okay. So ellipsoid indices texture. Oh, missed the double click. There we go. Right, so there's the pause button. Hop over to that new super lovely hash view. Hit pause and voila. So here's all the ellipsoids. So as you can tell, they're nice and rounded, right? Because this reflects the image we're seeing here on the screen. So they're all colored differently for each ellipsoid. So we can tell that, you know, so these probably differ just by like a couple of numbers or integer values. But because they're thrown through a hash function, they look dramatically different. Well, they're scrambled, right? So that's nice. Right. Cool, so now we have the visibility buffer being made. Now we can write more optimized shaders for it, because right now the current visibility buffer render for the ellipsoids is optimized for 32 pixels and more. So what we're going to need to do is write a we're going to need to write a specialized one for different sizes of ellipsoids. So we know their sizes, so we can, when we emit all of our ellipsoids into a buffer on the GPU, we can be like, how big is this thing? And if it's if its largest dimension is bigger than 32, we get it to use this shader by binning it into a separate bucket. So a separate array. And then if it's less than 32, we'll get it to use another one. If it's less than 16, we'll get it to use a different one, I think, maybe 8, another one. So we've got to have like a bunch of them, probably for every power of 2. I've just got to think about that. So the most obvious, so we can label this one 32 plus 32 squared plus. Now what we need to do is copy paste this code, and we'll write a completely different one for probably ones which are 1 pixel, because that, you know, maybe we should not render those ones, but you'll be able to render a lot of them quick. There's either don't render them because they're so small, or try and render them, but they might look bad when you render them. And half these won't even hit, probably. But the best thing about this sort of one version, so the way you can rewrite this, so rather than going over one thread group getting an ellipsoid, instead you get one thread group gets 256 different ellipsoids. And then you could probably do some sort of preload. You could probably preload into LDS memory as well, or something like this. But yeah, I don't know. Yeah, the idea is you would just simply, each thread gets an ellipsoid, does one reverse ellipsoid, and then sees if it hits it and then ends. So simply you would just get rid of all this. Don't really get rid of all that. So the ellipsoid index will be the dispatch index at this point. So that's the problem, is you've got to know, like, where do I get... You've got to get you're going to get the index within the bin, and then you go into the bin and get the ellipsoid index, and then you use that. Yeah, so the ellipsoid index will be something like bin ellipsoid indices. So you'd fish that out. You'd also probably say, like, you need something to say, well, if this has exceeded the bin, all of the ellipsoids that fit into this. Yeah, all the ellipsoids that are in this bin, if it exceeds that, then return. Fish it out, get the bounds, get the ellipsoid. Then, to calculate the pixel coordinate, it will simply be bounds min, because it's only 1 pixel, right? And then simply just, you know, if it goes outside the bounds of the screen, well, no, you don't need to check that ever because it's already checked earlier with a different shader. So it'll be pretty safe. And you simply just do the reverse Yeah, do the reverse ellipsoid there and then write it out to the screen. Voila, if it hits. So that will do 256 in a single thread group. So that's, but it only writes out single pixel. Maybe you'll be able to LDS preload, it might be better. Maybe. Not sure though, because they'll be they're not showing them across multiple threads, it's just each thread preloads its own ellipsoid and that, maybe not. Cool, so I guess let's get the stuff around the actual binning buffers and stuff and sort that out, because we've got these two different shaders now. We've got to build the intermediate ones because there's still more we've got to build. But we need to sort of like, how are we going to bin them in, make this sort of bin ellipsoid indices, and this is just called bin ellipsoids. Bit of a terrible name. So you probably want to make a new buffer just called ellipsoid bounds. Oh no, repurpose this one. That's a good point. So this should just be called ellipsoid bounds. An ellipsoid bounds buffer, much better. Now, when we have this GFX bin ellipsoid, we'll simply just repurpose that to screen bounds depth. So it's got some screen bounds and a depth. Right, does that still work? No. So that's in shaders, we're still, in shaders. Okay, so we'll just literally output bounds to that buffer now. Okay, let's keep going. Right, there's a dot bounds on there, so that is 4334. Nice, just keep going. Cool, now we've got this shader here that we've halfway through writing, so I think we're in a good place. Now the next thing we want to do is create another sort of system for, so we've already got a way of binning these ellipsoids. I just want to know how many, yeah, let's figure out how many of these different shaders we're going to need, because it's really going to dictate. So I want to have one for 32 plus, right? 32 plus will mean we need 6 bits, right? We're rendering 1, because 32, to represent 32 is 5 bits, 64 is 6 bits, but this one is for ones with 32 and more. So if we did all the way from 1 to 32 squared plus, that's 6 different shaders. So that's 6 different bins. I think we can manage 6 buffers with 1 million. So I'm trying to aim for 1 million, right? So 1 million ellipsoid indices at 32 bits each. So that's 1 million, so that's 1 megabyte, times by 6 different bins. That's 6 million. 6 megabytes. Times by 4 bytes each. So 6 fours are 24. So it's 24 megabytes just for all of those. So that should be reasonable to store into memory. So we're going to do a similar trick to what we did before in this sort of whole binning process. If you go into the shared thing, the other shared file, I've got an internal one as well. There's a sort of a bin, tile bin, object bins. It's for the tile binning process, there's an object binning thing as well. Yeah. So I won't bother explaining what that means too much. But there's a visibility buffer thing. Maybe we can stick it here. So there's the visibility buffer ellipsoid binning. So one of the ways that you can, like, we've got a maximum number of ellipsoids which are coming into the renderer, and if you try and render any more, it will just not let you. So we're only going to render enough model instances which can produce 1 million ellipsoids, and if we don't, and if we do more than that, you'll start seeing some artifacts, I guess, like things will be popping in and out. But maybe we can do something clever where we can avoid those. It'd be quite difficult because the GPU randomly dispatches its threads. So we'll have to see around about that. That is for sure. But I reckon we'd got some ways to fix it. So in terms of like, see, it's got this sort of million thing. But that's really just the maximum of ellipsoids. Oh crap, it's more than that, isn't it? A million instances. It says 128 million. Nope. I'm not doing that. Right, so let's look around for this million thing. Okay, so visibility, buffer, objects, capacity. So the number of bins that we want to mouse is 6 bins, right? You know, maybe we don't need that special thing. Just use the ellipsoid caps thing directly. Visibility buffer bins, 6 bins, bin from. This is when we're trying to bin. See, the other one was binning the number of tiles and figuring out how to sort of, how do we, because the shaders were specifically trying to duplicate objects for every number of tiles that they go into. This one is not tiles, it's more like we're trying to bin the amount, like it's largest dimension. So this is our largest dim. And you take the largest dim and you do this maths here. So you max it with 1, take 1. Get the most significant one divided by 2. That's because we wanted to cut off some of the low ones, wasn't it? But this one here we want to max it with 1. No take away 1 because we don't want to sort of get rid of the lowest one anymore. No divide by 2 because it's not powers of 4, it's powers of 2. I want. So get me the nearest power, give me the power of 2 index of largest dim, and then clamp that between 0 and 5. There we go. So that will figure out which bin it goes into based on the power of 2 sizing. And then the bin offset. So all of these sort of ellipsoid indices in these bins is going to be in one big buffer. And we are simply just going to have a macro to help us get to that start of that array. Right, so those are those super lovely macros to help us. Now we need to go ahead and actually create these bin buffers and get those going. So again, we've kind of done this in the past with those sort of tile bin things. So we just got to find where those get initialized and copy them. Oh, come on. And so graphics internal, so visibility buffer bin buffer. So these are the ellipsoid indices bin ellipsoid indices buffer. It's a big name, but it's descriptive, I guess. And then we're going to find the visibility buffer or initialize it, drop this one in here, and it's a very similar thing. So what we're trying to do is, all right, let's write this in here. Visibility buffer bin ellipsoid. I could just call it a visibility bin. That might be a bit of a shorter name. Yeah, let's roll with that one. A bit better. Because I think some of the debugging stuff it's gonna be off the screen or whatever, and it'd be silly to work with, you know. So if we take hang on a minute. How are these even allocating enough? Hang on a minute. Have we got a times by the number of bins here? What? How are these even working? Ooh. Oh. Oh, those are called bin ellipsoids, aren't they? That's the wrong one. This is the screen bounds. Ellipsoid bounds, that's what we renamed it to, wasn't it? Yeah, that'd be a good one to rename. Right, we're looking good, looking good. So this needs to have the visibility bins. So I should probably change these constant names a little bit. So let's get rid of the buffer things. So it's the number of bins multiplied by the number of instances or ellipsoids that we could ever want to render, multiplied by U32 because it's just storing indices in there, right? Cool. So when we have that, we should be ready to start sort of, so we can get the shaders, how the shaders will use this sort of bin code. But we would need to, yeah, do all the other stuff as well after that. Like actually binning them into there. Okay, so that's all initialized now. That's very good. So that's about 24 megabytes, as we saw, right? So inside the render is going to be, we do one dispatch for every single bin. And so we need access to the bin ellipsoid indices buffer, and it's just got a U32 in there, which points to the actual, it's a indirection table, right? That's the ellipsoid indices in there. So we already kind of had that, I think. Let's just have a look. So yeah, this one already did it here. But this one, the 32 squared plus, needs to go into this table here like so. Now it's going to be a little bit off. I think there's some sort of like bin offset thing we have to do, mind you. Let's figure it out for a second. Yeah, we've got to get the, yes, you have a bin index. So this is bin index 5 because it's the 32 squared plus 1, right? It's like, yeah. So we've got, and then we're going to be doing like graphics, visibility, bin offset, bin index, plus whatever that is, and that will get you. All right. So you can never overflow with that one, I don't think. Now the problem is with, just got to be careful, right? Got to be super careful. So that's bin index 0 because it's the, it's one for only 1 pixel. So that's the first bin. And we need to check if we go past the end. So to check if we've gone past the end, we might have to do a bit of magic. You need to do like a minus the offset. Wait a minute, why is that a... ellipsoid bin ellipsoid index. Yeah, I think we'll say that. So if that has gone past the end of the bin. So those are stored, I think there's like a sort of like a next index or something like that that we would usually use. Let's just find in a previous one. Yeah, tile bin next indices. So I would use these before. Yeah, this is what it looked like. Hang on a minute. Yeah. So this is one I've done in the past for the tile bin split objects where it duplicates the object many times. These shaders end up being quite quick, which was cool. So this one will be called the visibility bin next indices, passing the bin. And this is what we use to bump allocate slots into those bins. So if this one which will be this here. So bin ellipsoid index. This offset to the start of the bin plus the dispatch index. If that goes past the end of the allocated amount in that bin, then we will return there. So we don't overflow the array, read in invalid memory or into the next bin, basically, because they're all next to each other in memory. Cool. So that's good. It just means that we've made this new variable here. So let's go ahead and make those variables. So inside the graphics internal shared, there's a thing called graphics globals, which is shared between every single shader. So we can read, we can write to this thing. It's available everywhere. Jobs are good. And we want to be able to do something like this. Oh yeah, I aligned it to a cache line for false sharing. Yeah, why don't we call this cache line aligned count generalized name. Oh yeah. Cool, so we can now plop that there like so. And this is called visibility. Bin next indices and graphics visibility bins count. So now we have that in the global buffer. We just have to obviously initialize them to the correct values and actually start inserting things into there, which is cool. So I guess we could get started on that. Now let's get them initialized properly. So before we do any of this visibility binning, we want to make sure they're initialized to the right values. So there's this shader in the tile binning one where it is called tile bin setup, and it just goes over all of those globals and sets the next indices to be the offsets to the bins, and then we can just atomic increment this and get, bump allocate into them. So I think we just want to copy paste this and put it here as visibility buffer setup. So go over all the bins. Realistically, this could just be this, but I don't know. Let's just do that. Can optimize it later. So we've got to make sure we end up dispatching this thing. So let's just get the dispatch code in there now. So in visibility buffer init. So before that is called, we'll call the setup. So we don't pass in any constants basically. We rewrite to the globals. And we are going to call the setup. This only needs to be launched one group. 111. And voila. Right, so now those are initialized. The final thing to do is actually populate this visibility buffer bins with objects. So the problem is right now is I have a bit of an abstraction and I need to tear it down. So I decided when I was making the occlusion buffer that it'd be a good idea to do a kind of a pre-pass. So I think we'll just nuke this thing. So okay. Render models. Our lovely render models. This would tile bin the ellipsoids and then ray trace them based on what anti-aliasing technique we have. And it's all some custom compute shader that just does it all in there, right? So this is really great because they're all roughly sorted front to back into these tile bins based on the view space bounding box. And then inside these shaders, they are ray traced. We get 4 of the hits. We get up to 4 transparent hits and the closest opaque hit. And we sort those front to back properly based on the hit distance. And then run the material shaders on the material sampling code and generate all the nice pixels and put it out to the screen. So it's really cool. You can have overlapping ellipsoids that are transparent and there's no fighting on it at all. But obviously we're trying to write a more optimized. We're trying to see if there's a more optimized way to do it by doing this sort of atomic min renderer and making a buffer that we can use to construct a buffer that only stores the opaque ellipsoids in it. And maybe this will only be a transparent render in the future. But I decided, right, so we need a good occlusion buffer since we're kind of doing like a forward renderer. And we're doing, yeah, we just needed a good occlusion buffer to help reduce the amount of overdraw that we get as well. And on the ray trace as well to stop sorting too many ellipsoids that we don't need to sort. So I thought, you know what, this tile bin ellipsoids needs to be its own function because I use it to do a pre-pass for occlusion culling. Turns out that's too expensive. The best thing to do is probably just take the occlusion buffer from the previous frame and reproject it and fill in some holes. We haven't done the reprojection thing again yet, so we'll probably do that. But we might not end up doing it anyway. But the idea is we need to get rid of this code. We're not going to reuse. We're not doing this way anymore. I know that for sure. So we're going to get rid of this code. And then we're going to take that sort of tile bin ellipsoids and move that code out. And so now we've got the sort of prepare occlusion buffer, which simply just takes the previous frame's depth buffer and downsamples it. And if the screen's resized, it resizes the occlusion texture and clears, right? Cool. So in render models, we've got this. We need... Woodjilla, my friend, how's it going? Oh, yes, sir. Can you fix it with a for loop? Okay. I think this person's trolling. How's it going? A-Love. Welcome, sir. How are you doing? So I think we can take all of this and bring it back here. And now we can change these shaders however we please. So I'm thinking really the visibility buffer should be the thing which happens first. But yeah, we can't do that yet. So just gotta be. So allow transparency can probably go now. So this is what it takes to bin those ellipsoids. We we go over all of the model instances and emit the ellipsoid. So in this shader here, yeah, and then this is the tile binner. But this one emits the ellipsoids that we need to render. Right, hang on a minute, I need to... Right, so render dims is ggfx scene dims .xy. Tile dim is tile dim. Tile grid dim is tile grid dim. Allow transparency is allow transparency. Good, 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 good. Okay. Looking good. So we'll still keep all of this. I don't know why this is complaining for. Didn't delete any of that code. So allow transparency is going to go. Really be rendering to full screen anyway. Scene dims. So we shouldn't really need the render dims to be passed in also. So let's go to this shader, the one that emits the ellipsoids. And let's figure out how we're gonna... So allow transparency is gonna go. And this render dims thing is now just GFX global scene dims. I was doing that before, but the problem is the occlusion texture used to be generated at a smaller resolution, but now we just use the previous frame one, right? So as occluded can now just use nice. So this is where we go over all the ellipsoids and bin them. Now the issue is so this bins them into those. Where is it? Oh, this doesn't do the binning right. The binning is done by the tile binner to figure out to splat them. Okay. Right, I think we need another shader that runs after this then. That goes over all the ellipsoid bounds and figures out how to put those into bins. Oh. Yeah, we need another shader. That's okay. So we want to call it visibility buffer bin. So we can call this bin setup, and then we call it bin or bin emit setup, bin emit. See, this is all to do with like the ellipsoids though. Should have dropped the ellipsoid. Because technically, right, we could put, you know, it's only for ellipsoids, this visibility buffer. Let's drop the word ellipsoid from it. So visibility buffer bin emit. So the job of this one is to go for all of the screen bounds, see how big they are, and put the ellipsoid indices into those bin arrays, and then populate the indirect arcs to dispatch these different visibility buffer render compute shaders. Yeah. Awesome. I think we'll be able to get this all punched up today. That'd be cool. Right. I'm just going to take a quick little break and then we'll yeah, punch the rest of this code in and see how well it goes. Right. BRB. Right, welcome back everyone. So let's carry on with this shader. So the idea is that we now have a buffer filled with all the screen bounds for each ellipsoid, and we have a buffer, another buffer filled with all of the ellipsoid information like its transform and material and everything. But we need to bin these into different arrays such that, or the indices into different arrays such that we can dispatch different compute shaders which are optimized for rendering different sized ellipsoids on the screen. So, right, let's quickly just drop that. You know, so you can only put ellipsoids in there. I wonder if we could do other things in the visibility buffer. I don't know what else we would do. I only want to render ellipsoids for this renderer. Maybe we'll drop the word ellipsoid from it because it is getting a bit long, you know. Alright, I think that's better. So back to shaders. So here's how it's gonna go. Oh, come on. What we're gonna do is make a new set of bundle constants that are uploaded from the CPU to the GPU, specifically for the shader dispatch. And we're just gonna take, so it needs it's gonna write out into that, to this one basically, this bin ellipsoid indices all the way. And then it's gonna read from the ellipsoid bounds. And that's it. Doesn't need anything else, because the index of the dispatch will be the index of the ellipsoid. And it should be as simple as that. So what we would ideally want is probably about 256 in the thread group. Let's check the chat up there. There we go. 256 in the local thread group. And so I've got to remember like all the tactics I did for the previous one. Yeah, we might have to, yeah, let me just go and grab that code. There's a very specific tile bin thing. Ellipsoid tile bin object bins. This is it. It's pretty clever. It's all the good crazy stuff is in this function here. Calculate insert index. So what 256 threads here in the thread group. And the way it calculates, yeah, this is the secret sauce. It's looks a bit like magic, but we'll go over it, don't worry. So remember that ultimately what we're trying to write into is, for crying out loud, what are you? This bin ellipsoid indices buffer, but it's not just an array of ellipsoid indices. There's 6 arrays in there, right? Because there's 6 bins. And each bin has a size of 1 million ellipsoids, right? So there's 6 million ellipsoid indices in there, which is about 24 meg. So when we calculate an insert index into that, we're finding what bin we're going into and which offset into the bin. So this code here is doing that in a very efficient way for 256 threads, which are trying to insert into completely different slots, right? So what we first need to do is get the screen bounds. So we've got the ellipsoid bounds here, and we're going to use get the ellipsoid index. That's the other thing we need, because that's the thing we're going to be inserting. And that is going to simply be the dispatch index, right? So we get the ellipsoid index, so the bounds by passing the ellipsoid index, done. Now what we're saying here is, wait till every thread in this 256 has got here, because these run in lockstep of 32 threads at a time. So we've got, I don't know, 8. Is that right? Yeah, 8 times 32 is 256, isn't it? So we've got 8 waves of that are running in different, they start at different times and they run code and they're on different compute units, or on the same compute unit, just one has already ran and has been put to sleep. The control barrier will say pause here until all of them get here. Now we're gonna all threads bump the object's count in LDS memory. So we need a bit of LDS memory here. So we'll get that at the ready. Dispatch group. So this is shared between all of the waves within the same thread group. So GFX visibility buffer bin emit. And that is going to be some kind of structure. Visibility bins count. Okay. So how many objects and the base star indices? One for each bin. So what we're trying to say is, so for every 256 ellipsoids that we're trying to render, they can actually insert into different bins. So we're gonna, like this sits basically right next to the compute unit. So doing an atomic add here is not that bad. So it's quite cheap in comparison to it to main memory, because it's like an L1 cache versus main memory. And the other ones are probably, the other compute units are probably, I think on AMD hardware you have a dual compute unit. So if you're running in Wave 32 mode, they could access the same LDS memory at the same time. But on other hardware, you don't have that. I think from memory, that's the way it is. So this will be nice and quick. We'll get a relative index that we'll jot down for later. So essentially just figuring out how many, let's get this right. I was jumping ahead here. Right, now we're back in. So we're just figuring out, right, how many of the 256 threads put into each bin. Now, there's this thing called an atomic adder index. All this is doing is saying, because we might not have every single thread active right now, and this is a good point. I completely misspelled that word wrong. Oh my days. Okay, so if the ellipsoids index goes outside the number of ellipses that we've actually tried to render, then return. Now, so this atomic adder index is just saying, all we need is 6 threads, because we've got 6 bins, right? All we need is 6 threads to try and atomic take these object counts from this sort of L1 memory in an LDS, right? And atomic add that integer with the one in global memory. So rather than doing it for 256 times on the same integer in main memory, we do it locally so it'd be quicker, and then do it once for each thread group of 256 threads into main memory. And this will help with performance basically. So this just reserves an atomic adder index if the atomic adder index goes within or if it's the first like 6 threads, basically, we figure out how many active atomic adder threads we have, then go over all of these. So in a good world, this loop only executes once, and in lockstep, there'll be 6 threads running this code. But you might be at the case where you're at the end of the render ellipsoids and you only have like 1 active. So in that case, it'll run 6 times, unfortunately. If you only have 1 active though, you might as well write it out to main memory maybe, and then not do any of this. Yeah. Maybe. You can't, yeah, maybe you figure out how many threads are active. And then you don't have to do this silly crazy crap. Yeah, maybe that's the better way. Right, I've got me some ideas now. Yeah. So the way they make this code cleaner, easier to read, is you just say active. No. Because that would be, this is across. Yeah. Active threads count. If that is less than or equal to the number of bins, then simply just take the bin that you're trying to bin into. Oh, we didn't change this out. So the bin that we're trying to go into is visibility buffer, bin from largest dimension, and you get the max element of a so we take the dims, which would be the subtract. We want to get the sub float 32 of bounds max point. Take bounds dot min point. We're then going to add 1. Because it's inclusive, isn't it? Is that right? No. Yes, it might not always be a pixel, but it should have discarded it if it's small enough. And then, yeah, so I guess you say 32 cast. Okay, that'll be right. Then you get your largest dim. That'll be max element. So max of xy. Nice. So this is like, gets the nearest power of 2 and figures out which bin to go into. Now, right, so based on the amount of threads that are active within the thread group, but they should be always be within the same wave. Anyway, They all go into here. Those ones just write directly to global memory. Write directly to global memory because there is not a lot of. There is less threads than there is bins. Yes. So the bin index. So your insert index is going to be atomic add directly into. Cool, so this is visibility. Visibility bin, next indices, oh yeah. So bin index, and you're doing it for your thread, so it's just one. So if you happen to hit the same one, whoops. If you do it six, yeah, but you might do it 6 times on the same one. So it might be better just to keep the old code actually, yeah, screw it, let's keep this code. So based on the thread index for this atomic adder, we're figuring out how many active threads that we have which are going to add to the global memory from our local LDS memory. And loop, hopefully this only runs one time, but you could have less threads that are active than 6. So it might run a couple of times or more. So we get the base bin index, add the base bin index with the atomic adder index, that gets you your target bin index. Then if it's still in bounds of the bins, you simply get the number of objects that you've... Oh crap, I've got to change this. You get the number of objects. Gotta look out for this tile bin thing, it's all over the place. Hey Badnu, how's it going? Welcome, and Batman. Did one-to-one correspondence to assembly machine code? I guess you can see what it translates into, but yeah. But it all depends. Compiler optimizations and all. Question from a gamer: how does a game developer feel if your game gets pirated? Because being honest, I have done many games. Well, so right now I have not released a game. You know, piracy is a weird one. You know, it's obviously a sin. It's stealing. So that is wrong in and of itself. So obviously you shouldn't do it. But the fact that it happens is, you know, the fact there is sin in the world, it means you need to handle for that. So if someone steals your game, maybe you have ways, incentives for people to still pay money even if they pirate it, right? Or maybe you don't care if people pirate it and you know, because you're just making a piece of art and it's something you do in your spare time. Or you provide a PC release where the PC release is the one where it's like, okay, this one will probably get pirated, but we'll get some sales. And then you do console releases where these ones are less likely to get pirated, and you'll get more sales. And the people who pirate your game on the PC will hopefully be converted into some kind of community advocates in a way. They really like your game, they love it, but obviously they don't love you enough and they steal your game. But they hopefully help spread the word about how great the game is to other people, and other people buy it on consoles, or they are at least people who are around to maybe keep your game community active enough, and it becomes a more sort of enticing community to be in. So that's the way I would logically think about pirates and how to deal with it as a developer. You've got to just be aware that it exists, but I wouldn't try and protect yourself against it, because it makes the user experience worse, and people are just going to get around it anyway in the future. So yeah, in the past I have pirated games as well, but I do obviously regret doing it because it's not a good thing to do. There is a bit of a sad place in games where games are becoming less and less available, and the only way to access them is through pirating them. And it would be nice if there was some kind of legal thing which made it such that if companies do not look after their products and want to sell them fairly, then there's some legal way for you to access copies of that game. That would be great, I think. But obviously, politicians don't really know much about video games, so I doubt that thing will ever get done, If I was a small indie dev and I poured my heart and soul into a project, I might be sad if I pirated my game. But if I was a worker at a big company, you wouldn't care. Yeah, I would, pirating is bad, but I think the way you, like, see, I do care that people pirate games, but I wouldn't care enough to tell them they're bad people. It's a me problem, right? I should know that people are pirating games. What am I going to do about it? Right, but I'm not going to put terrible crap in the software to make the user experience bad for everyone who's paid real money. I'm going to be proactive and figure out what can I do to actually make them pay still, or what can I do to help them actually help me. Have a bit of a trade in a sense that they don't even know about what's going on. How can we drive the pirates to be helpful? How's it going, Isaac? How you doing, sir? Welcome. Hope everything's going well for you. Copying code's fine, but pasting code is probably one of the most dangerous things you can ever do. Because you just don't read it back and be like, oh, I've got to replace that thing, and that thing, and that thing. You just instead paste it in, job's a good one, run the code, and then cry when it breaks randomly. The worst ones is when it works fine, but later on down the line it crashes and you've forgotten you copy and pasted the code to begin with. Alright, it's this line here, wasn't it? Don't know why I'm using the mouse. I got these keys. All right. Cool, I think that's all right. So we atomic add from our LDS memory into global memory, get base insert indices, wait here for all the waves to get here, fish the base indices out, add our relative index, which we said keep an eye on that earlier. Right, the relative index from the LDS memory, accumulating that counter. Finally, we subtract the bin offset. And if we go outside of the bin, it means we have overflown it. Cool. So this means we overflowed the bin. So we cannot insert this ellipsoid. It's just a safety measure. Now we're on insert index. Finally, BC bin indices, insert index. I'm good, thanks. How's the project come along? Yeah, it's come along well. We're just trying to figure out, can we render more ellipsoids, basically? How many ellipsoids can we push to the screen? So I'm trying out yet another renderer technique called a visibility buffer, where you just render the depth and the ellipsoid index. And with those two pieces of information, you can reconstruct surface normals and do material shading, because you can do the ray and the depth and use the ellipsoid index to get all the material properties and do your material shading and stuff and get the normal. And it seems like the performance is somewhat comparable at the moment, and it might be better. And it just renders opaques. It doesn't render the transparency. So I think we'll still keep the tile binner that we've been writing for transparency, because it's actually really good at that. Because you can have overlapping ellipsoids and they don't Z-fight at all, and it's pretty cool. And they're all material shaded. You've got custom anti-aliasing for those things, so you can make them look real good. But I reckon we can do a better job at the opaque renders. Because the problem is when we push 1 million ellipsoids through the renderer, when we try, 900,000 of those get occlusion cold, and then we've got about 100,000 going through the tile binner, and that takes 1 millisecond just to tile bin them, and then it takes a further more 6 milliseconds to do the rendering on them for 100,000, which is alright, but I reckon we can do better. So we're instead putting a little quad around each ellipsoid, and we're just doing an atomic min 64-bit into a buffer, because textures have terrible cross-platform support, whereas a buffer with a texture with 64-bit atomics doesn't have as good support as a buffer. And I tested it out, and turns out the performance is about the same, which is interesting. I didn't realize it'd be about the same, but it's on AMD hardware. We've got to maybe change it. And yeah, we might have to do some custom swizzling or something, because it's not it's not swizzled like an image is in memory. But we can do this atomic min with our depth in the higher bits and the ellipsoid index in the low bits, and construct a image inside of or a texture inside of a buffer that we can then fish out later and do the material shading. So we're writing this tile binning. We've just written this tile binning shader. Sorry, ellipsoid binning shader, where it bins the ellipsoids based on how big they are on the screen. And then we have these optimized shaders, which will specifically render a 1 pixel ellipsoid, a 32 squared plus ellipsoid, and we've got to write the ones which happen in between. So they're hyper-optimized shaders for specifically ray tracing against different sized ellipsoids on the screen. That's what we're currently working on right now, and I think next stream we'll have it all working and material shaded and everything, and it'll be proper up and running. We're getting very close this stream though. Presumably, since you can just all in compute, you don't get any of the depth rejection stuff. I guess if you did visibility buffer, it wouldn't be too bad. Those not much more expensive than any kind of depth prefast, presumably. Yeah, so exactly, we do not get the early Z. That is true. But we wouldn't get the early Z anyway in a pixel shader, because the pixel shader would have a discard in it. Because when we render a quad around, we'll render a quad in a pixel shader, right? And we'll say, hey, does the ray hit the ellipsoid? If it doesn't, we do a discard. So it's kind of the same sort of thing, but I'm just doing it compute. And so I've got to do this my own sort of tile binning, if you will. Sorry, I've got to do my own binning where I have a very specific shader which launches the exact number of, what can I say? Yeah, launches the compute shaders in such a way where it's good at handling quads at specific sizes. So if we had a bunch of 1x1 squared ellipsoids, or even, yeah, something like that. But these ones will probably look terrible. We might get rid of this one. This would be faster than a pixel shader, because that's what they do in renderers where they render like triangles, which is sub-pixel, because you don't, yeah, you have like that quad occupancy thing. But yeah, the visibility buffer will get overdraw still, that's true. So the way we still need a good occlusion buffer. So the occlusion buffer will reject ellipsoids which are too far behind other ellipsoids from the previous frame. Maybe re-projected and stuff like that. We've still got to iron out those kinks. Right, so we've just written this guy. So let's get it dispatched, and then we've got to write another shader, which is gonna fill in all of the indirect arguments for the other guys. So let's go full ham, and get these things set up. Interesting. Did I get rid of... I called it emit setup, did I? Okay. So graphic GPU sync resource. So visibility bin ellipsoids buffer. What else goes in here? Okay, so that's sync resource read write. So write out to that one. Good. Nothing else in there. Next one is the ellipsoid bounds. So that's read only. Okay. Do we do any globals? We do rewrites globals. And we want to dispatch this indirectly based on how many ellipses that we're trying to render divided by 256. Now, yeah, I guess we're going to need that as well. So it's offset of graphics indirect args, visibility, buffer bin emit. Cool, so we get that one all filled in. So we're going to need one like this as well, where it's the bin. I guess I end it with args all the time. One for each type of binning shader. Okay, so it gets launched indirectly, but we've got to actually fill this in. So this actually needs to GPU indirect args buffer, just rewrite to that. So in the setup, we are going to say graphics indirect args, plop that in there, and then say U32 3, yep, graphics global. So render ellipsoids count divided by 256, but it's not just divide, right? So it's one of those core divide roundups. By 256, please. 1 and 1. Nice, so that is the indirect args for this all set up. Very good. I wonder if I got the sync code right for those other shaders. Opaque, which bugger did that? Oh yeah. We can get rid of that now. It might be nice to know some of these things. But yeah, that's good. Oh yeah, so this one, I want to know if we did do the right sync code. That's good, that's good. Cool, so that's the shaders. Any other indirects that we need to sort out? So after this visibility buffer emit, what's it called buffer emit? It's bin emit. Huh. Yeah. So after this one, we need to make another shader. All these shaders, eh? Which will emit. Oh, awesome. Yeah, true, but that's the same for like a classic diverter renderer too. You also get overdrawing the G buffer pass, but since the frag step in the G buffer laydown is relatively cheap, it's still worth it. Visibility buffer should be even cheaper. Yeah. Right. Yeah, because you're just writing out the albedo. Yeah. You're writing out like albedo, surface normal, and depth. Maybe other things. Yeah, that's true. Yup. That's right. Yeah, it's less bandwidth than a visibility buffer. So this would be known as the bin or render setup. Interesting. Okay, so for the render setup, we will have dispatch args for each. Render args, we'll call them one for each bin. And the way you calculate these, just gotta, hang on a minute, see if I can find the other one. Alright, splat objects, this did a similar thing. There's something like this maths here. Let's just copy all this and rework it out. Right, so I just launched it for the number of bins. That's another way to do it. It's more effective. So you get the bin index, you get the number of objects, or the ellipsoids count, I guess. Bin ellipsoids count. So visibility bin. What do I call it? Visibility bin next indices. Yep. Take away the offset. So now we min it with the maximum number of objects. So model ellipsoid indices. Hang on a minute, did I change the wrong constant? No, model ellipsoids. Crap, what was that encapsulating again? Hang on a minute. I wonder if I bugged something up. Git diff source graphics. Ah, you bugger, I did bugger it up. Because that used to be models capacity times by 128. Right, hang on a minute, let's correct this. Graphics models cap times 128 now. So we do kind of want a sort of ellipsoid's capacity, I would say. In general. And that's the one we want to be using instead. So let's just quickly find all of those, ladies and gents. Oh, for... Oh, okay. I'm going to do a shift R instead of a dot in the editor. I think so, at least. Don't know why it wasn't working. Right, so that's the number of model ellipsoids. Yeah, that's fine. Yes, the allocator for those, that's alright. Next one. Okay, that's good. Corrected that. Right, that would have been a crazy thing. I didn't realize that. Cool, so back to here. I'm going to use our ellipsoid's cap. Clamp it between there. Well, oh yeah, because we can atomic add and it will overflow, but we've got a minute here. Good. So this would be known as the sort of visibility bin object, bin ellipsoid counts. Just chuck that in there like so. And then, now depending on the shader that we have, so these specialized shaders, we've got to obviously write the arguments in differently. So this one here, which is 1 pixel, does 256 at a time. So we've got to take this here and divide by 256. Then yeah, we might just do a switch statement. I'll do this sort of if thing. But anyway, the one at the end. So that's if it's equal to 0 actually. We'll see how the rest go. The one at the end, which is the 32 squared plus, that one needs to do 1 thread group for every ellipsoid. So you just plop the whole thing in there like that. Cool, so now we've just got to write all the in-between shaders. Hey, Mr. Shelby, what's up with your compiler? Production ready yet, innit? No. So it's production ready for me because I know the source code, and when there's ever a problem, I can go and edit it. But for other folks, I guess it's good enough for a lot of things. You know, definitely good enough for 2D stuff. You know, I've been using it for a 3D render and I've written quite a lot of things in it. There are some limitations with it to do with how you sort of like return stuff from functions. You got to return whole structures and stuff, but things get inlined anyway. It's not a big deal. It's just a bit clunky when you use it as a user, not really by the code that's generated. But there's lots of benefits from it, in which that the code is a lot nicer to work with and share between CPU and GPU. Obviously, the operations on the maths is a personal taste. If you like writing functions or operators. And what else? It only supports Vulkan right now. So if you want to target a different platform, you'd either need to write a different backend for the compiler, and you know, for me, I could do that, but someone else will have to get in there and do it if they want to do it for, you know, transpile out to a different shading language for other platforms. But yeah. But yeah, it's good enough for me. But yeah, what I built the compiler for is for me, and I guess if someone was super interested, they can get and use it as well. But it's mainly just to show to people that why aren't we programming in the same languages we write code in on the CPU? And for some reason that has never been answered well enough. I don't know, I get people who are like, you want a domain specific language for writing shaders. There's like people who are like proper like shader people, you know, they just write shaders and they want a domain specific language, but you just write, you know, reading and writing variables and doing maths, like, you know, reading, writing memory, doing maths operations, like a systems programming language has that. Why don't we just use a systems programming language? You know, we can, you know, these newer languages, especially like Odin, they have like, basically they have arrays which you can do swizzling on it, which is pretty cool actually. I do like that feature. You know, so you have that domain specific swizzling that you want. So like why aren't we using these? Why aren't we able to share code and structures and stuff? And that's what I want other people to be doing. I want this idea to be stolen. I'm just going to sit here and live in the future. And I hope everyone else gets to live in this future sometime soon. You know, I got printing from shaders. Look at that. I can render objects from shaders. That's not really a feature of my language, but yeah, the printing is. Or compiler, should say. Right, should we write some extra specialized shaders and see if we can get this thing kicking off? So we've got to write one for 2x2s as well, I think. So this is like chord size. I don't know what I'm going to do for a 2x2 one. So we've got a 2x2 on the screen. Do we just do 256? Launch 256, preload, and do a for loop, a 2D for loop. Do we take every... Nah, just take the quad. Yeah, so I think we want to say dispatch index divided by 4 or something like that. So you launch so this one will get 4. Each thread gets an ellipsoid and tries to write one shader for rendering an ellipsoid which takes up at most 1 by 1 pixels. Each thread gets an ellipsoid and tries to write a pixel. If it tries to write a pixel. Right, let's get these comments because future me or other people looking at the code will be questioning what is this doing. For at most write 2 by 2. Right, each thread. So we want to say every 4 threads gets an ellipsoid. Every 4 threads gets an ellipsoid and tries to write 4 pixels. Okay. So we do a divide by 4. They'll all fish out the same ellipsoid index for 4 threads. Right? Get the bounds, get this, right? So this is where we may benefit from some LDS preload because there's 4 threads which share the same memory. So we're going to try and say to do LDS preload because 4 threads are going to share the same ellipsoid, so it might be worth, I don't know. Might not be though. Ray trace against the ellipsoid. So many little ray tracer shaders, damn it. And then if we miss, continue. If not, write the pixel out. There's some things though with this. We swizzled it. No, we haven't swizzled it. Oh, wait. Yeah, this is true. We've got to... So because we're right now in this sort of flat array, I think we might just want to say add. Oh, no. Yeah, so we're doing like... add U32 times 2. We want to take that sort of local index. Mod 2. Is that right? So every 4 threads. So mod 2 that gets me the X. Right. Yeah, then divide by 2. When we divide by 2 though, you gotta AND it. Yeah, so I guess if you just AND 1 for that. For the Y, you need to AND 3. Because that will get you the first 2 bits, which can represent 4 different values. And then you want to divide that by 2. So that will offset the quad. I think, at least. Yeah, so for 0 and 1, that will get you 0. And for 2 and 3, they'll get you 1. And obviously, everything above that will just be ANDed out, so it's always 0 to 3. Cool, so that'll get you your coordinate. And now you render your ray tracing and put that out to the screen. Cool, so that's the 2x2. So when you dispatch that one, I guess we can put this in a switch, to be honest. And it'll probably just go through all of these anyway. So this one was for 5, wasn't it? So this new one is 1. So I guess I can do 1 by 1, 2 by 2. So this one, we're doing 256 launches, right, of threads, but we need to launch 4 times as many. To get that to work, right? So we need to multiply that by 4 then. Nice. The next one is a 4x4. How might we optimize that shader specifically for a 4x4 launch? So it might be quite difficult to test all these and performance and stuff, but I got some ideas. we'll probably just have like a nice flat ground and get a fixed camera angle. That we just try and tweak these things and relaunch it, and I think we can do a good job that way. So this next one is rendering at most to 4x4. And I forgot to change that bin index here, so it's bin index 1. Bin index 2. So what should we do for this one? Should we do a similar technique, right? Every thread gets 16. Right, in this case you must benefit from LDS preload maybe. Maybe it might be better to make this a higher number like 1024 as well. That's something to play about with. Sorry, File, that's a shame. How? Yeah. Are you working in software development as well? What sort of job you got? Yeah, I got the day off tomorrow. I booked it off. Go to the gym with my wife. We're gonna have a nice time. Gonna exercise. And then, yeah, relax. Gonna be nice. You recently signed up for the gym again. She got me a free day pass, so we're doing that. A nice activity. It's gym day as well for me anyway. You know, exercise 2 days, every 2 days. You know, I think, well, 2 to 3 days. It's gym day tomorrow. So yeah, we'll do every sort of 16, right? Okay. That's interesting. Reloading to LDS, maybe? Yes, please. Maybe that will be better. So this offset here, how do we do it? So if we take, what I'd like to do is take, so 16 is how many bits? So 3 is for, yeah, that gives you, right, how do you represent, so 3 bits represents 8, obviously. So I want all 4 bits on. Yeah, so that'll be 15. So if we end with 15, that doesn't get you the X. To get the X, you need to mod with 4. Now the compiler will optimize that, so I don't really mind writing it that way. You know, I could have done a divide by 16. But anyway, there we go. So we still do this and then this time we divide by 4. So that will get us the offset. Yeah, there's lots of little bits of hand optimization we're going to monkey around with, but I don't have to do amazing at it on this first pass as long as this ends up being better than the existing renderer, then we know it can be better. Then I can just sort of do all the optimizations that I can think about and then just leave the rest for later, all the little tedious ones. So that looks like it's all right. Yeah, I like that one, that's good, and we write that out. Okay. So that's the 4x4. So that is 16. Yeah, we've got to be careful doing that. No, I think we could be okay. So 8x8. So 8x8 is 64. Are we going to do a similar thing again? I think we might be better off like dispatching 10. Like we could. Yeah, I don't know. We'll have to monkey around with like quite a bit. But it might be better to, at this point, start just dispatching a whole thread group for this thing. Oh yeah, no, the LDS preload won't make any sense. No, those LDS preload things won't be good enough. I don't think. Because you're not processing the same data on different... what's the way of saying it? No, they might make sense. Yeah, let's have to test it out. But it won't make sense for the 8x8. So the 8x8, I think I'll just launch a whole one of those. Yeah, so I think from here, they'll be the same basically. So 8x8, 16x16. Hang on a minute, do I need 7 bins? Crap, well, I'm glad I'm writing this out. Yeah, I need an extra bin. Bug it up. 1 more bin. So 1x1, 2x2, 4x4, 8x8, 16x16, 32x32, and then 32x32 plus. Nice. Cool. Pretty good. So let's just make those ones. So I think then 1x1, 2x2. So this one will need to launch. This is the 8 squared. I'll write plus in there, that's really dumb. Nice. So 8 squared. So this you need 64 only. And I guess I could do the Morton Swizzle 8x8 thing on it maybe. So yeah, the group index will get you the offset instead. Each thread group gets the whole ellipsoid. You preload that, or you load that in. Then this used to go over every pixel in skipping 30 groups of 32, but we don't need that any at this point because you'll have all 8 threads active, which will just process the 8. Sorry, all 8x8 threads active, so you just process all those, right? So we just gotta shift this code out of the loop and so the local chord is a Morton Swizzle. I guess we'll keep that. And from the XY, from the min point. And then if the min point goes past the max point, we just return. So that thread goes inactive, doesn't try and do anything. And then do the ray trace. If we miss Again, do a return. And then do the atomic min if we pass with the ellipsoid index and the depth in the high bits. Cool, so basically the other shaders are going to be like this. Hang on a minute. Do we need anything special? I don't think we do. So I think this one here, this would be the 8 or 16 or... So I'm thinking, right, do we need to hyper optimize these any differently? I don't think... Oh, no. Right, so I think the contents is going to be the same. It's going to have like a hard-coded bin index, and the local parameters will be different. It's a bit of a shame, but I guess we can change the code if we need to later on. So it's going to be a bit of a copy-paste job, and then... So 8 by 8 is 64, right? 16 by 16 is 256. And then 32 by 32 is 1024. So make sure we get these bin indices right. That's there. So that's the 32 squared. There we go, finally. So that's all of the shaders written out. It's a lot of shaders, but these should be hyper specialized for these types of renders. Cool, so I think we're in a good place there. The next thing we need to do is actually write the dispatch code for this. So that would be graphics. So we've done this in the past. If I search for tile bin something, we should find it. Here we go. So it's something like this. That's what we want. So we find what we call this function is the visibility buffer is kind of around this code anyway. Right, here's the visibility buffer. Maybe we should put this in its own function or something. Getting a bit long. So basically before... Right, so we start the emit by preparing all of the atomic integers which point into the bin buffer for each bin. And then we bin all of the ellipsoids into those bins based on how big their tiles are, or their bounding boxes are on the screen. Then we launch different renders. So this is where we get all of these guys in here. So there's a 1, 2, 4, 8, 16, 32 squared. Nice, so there's 7 of those. So let's look for everything tile and replace all of that. So go over all the bins. And then we run this render. So be careful here. This is the visibility buffer initialized, so it initializes it to its maximum value of U64 max. Then we should put this code inside here. I thought I removed the word ellipsoid from all the things, just to make it a bit shorter. Oh, I don't need to do that anyway, so it's render, shaders, bin index. Now we just got to be super careful. So this would be the visibility, render args, bin index. These have been populated by... Yeah, what have they been populated by? Have we not got that shader dispatched as well? Is there a render? Oh yeah, it's here, isn't it? Put that there. The render setup, we haven't called this yet, which sets up these render arcs. What's the name of this song? This is Stone Rebel. I think it's a group of people. They always release albums like every month. It's really cool. So they've just got tons of. This one's called Lost in a Deep Breath. It's 21 minutes, 34 seconds in. And here's the playlist. Yeah, they're pretty good stuff. Yeah. Crap. Okay. Right, so nothing else special in there, I don't think. So we've got to be careful, but I think we can do a no overlap here. The problem is there's going to be barriers inserted if we don't put no overlap in there. Because you can we're atomically writing to that. So we want to make sure there's no barrier that's placed down in between all of these different versions of the same shader which are running. Cool. So I think that's everything. Yeah, so that was just a copy of... Right, that's good, that's good. So we've got to actually do another setup shader. So many setup shaders for this thing. And this one is... And we are just reading and writing to the globals. Yeah. It's writing it. Yeah, let's do that. Nice. Cool. That will be do all the rendering, and then we have a debug renderer because we only render out to a buffer, just so we can support more platforms. Because 64-bit atomics on images are they're quite unsupported. And then we can split them back out into two textures again, and actually view them in the texture viewer that we've got in the game. So that's cool. Right, so that's all of the code basically written out. There's probably bugs, but it's basically there. So now it's just a case of... It's just a case... It's just a case of trying to get it to run and seeing what happens. But I guess that's a bit too much for today. So the next stream will be on Thursday, about, I guess, how long does the stream be rolling for? 3.5 hours ago, there's the maths. And we're going to get the visibility buffer working and actually running. So we had it running in the past, obviously, but we're going to be running it in this more optimized version and then tuning the results to see, can we increase, like, how fast is it, and can we increase the performance by changing the shaders just a bit. And then we'll do a material shading pass after the visibility buffer, which will actually render the materials of the ellipsoids for every pixel and make it look like the current ray tracer that we've got for the tile binning ray tracer. and then just compare the performances between the two and gauge whether this visibility buffer is actually faster than tile binning all of the ellipsoids. And we're not just going to do a very fixed screen. We're going to be doing probably ellipsoids going off into the distance, and maybe, yeah, just some ellipsoids going off into the distance, I think. And maybe we'll spawn some more ellipsoids on top of those or something. We'll see. So we should have larger ones going off into the distance with smaller ones, and really see the power of how good the visibility buffer one is, all these special shaders, and also how the varied ranges of sizes of ellipsoids impacts the tile-based renderer, where it emits a whole bunch and then sorts them into screen tiles and, you know, tries to render them, and just see where, just compare them and see which one's better. So yeah, that'll be next stream. We'll probably have another stream actually where we'll be doing a bit more tuning on the Sunday. But then hopefully that'll be that part done. I don't know what else we've got after that. Let's have a bit of a gauge. Because we've gone on a bit of a detour just to sort of... We're in the process of just trying to see how many of ellipsoids we can put on the screen, isn't it? But if the visibility buffer... So we're in this stage right now. Test high number of model instances. If the visibility buffer is something we want to keep, we're going to need to probably do a different anti-aliasing pass specifically for that image. Because the ray trace anti-aliasing, sorry, the ray tracer has like a ray trace anti-aliasing, super sampled anti-aliasing, and a multi-sampled anti-aliasing. So we're going to need some kind of anti-aliasing to at least make our image not look terrible. And I guess that would be part of the performance measuring as well. And then after we're done with this sort of thing, we'll be trying to render out HDR, do a tone map and bloom, that sort of thing. Cool. So I guess we'll be working on this anti-aliasing thing as well until the end of the month. Nice. Right, let's find someone to raid. And yeah, feel free to join the Discord. It's in the About section of the channel. I wonder if there's any other C or C++ people on. I always find them really hard to find. Well, I thought this guy usually programs in C or ++, but maybe not. Right, I might just bail. Oh, there's a Jai guy. We found a Jai guy. Yeah, why aren't I following this guy? I've read him so many times. Kuju. Is that like a play on? I want to knock. I don't know what knocking is. Right, here we go, guys. Okay, have a good Wednesday, guys. Hopefully see you all on Thursday. Good stream so far. We got all that code written out. So hopefully, you know, next stream it just runs first time. Maybe not. Right. Have a good one. Catch you later.